Okay. Okay, then I think let's start with this topic, state space problem. Uh, Previously, we were finished with this P's. P's is for performance, environment, actuators, and sensors. And now this is state space problem. So you will read this term in AI, which is state space problem, or shortly SSP. So whatever normally you have a problem, then normally that problem, especially in computer science and in AI, that problem will have some initial state and then some final state or goal state. And then you can start from the initial state and you will have some strategy. And by applying that strategy, you will go from initial state to the next, from that next to next, and so on. And then until you finally reach on the goal states. So between the initial and goal state, you will have a finite set of states on which you will apply finite set of actions. So in a problem, you have some initial state and then final state, and in those states you will have other states, and from the initial state you will apply some action and then you can reach on the next state, and then you will apply some action and then you will reach from that state to the next state, and so on. In this way you will reach on the final states. So that's why in each problem we normally have an initial state, we have a final or goal state, then we have a finite set of actions. These actions you will perform from one state and then you will reach on the other state. So then there is a transition function, or you can say, so you will have actions and these actions will make you able to transform from one state to another state. And if you have a problem like this, which will have these different kind of entities, then this is called state space problem. Then this is called state space problem. If it is difficult for you to memorize this sentence, then you can have this picture in your mind. So you have a state space, and then state space has a starting state and the final state, and then you can perform set of actions, and for that set of action your when you will build some algorithm to solve that problem, then your algorithm must have the an action function. An action function will do what? Which will perform action from one state to another one. So shortly, you have a start state, end state or goal state, and a set of actions and a set of states, different states between the initial and the final. And when you will move from one state to another state by applying some function, it will cost you. And that's why you will have a path cost. And path cost means when you will move from one state to another one, what cost it will occur there. So these are the things. If some problem will have these things, then that problem will be called state space problem, or any problem that you have, you will face in future. For each or for any problem, you can identify these five things. You can identify these five things. And when you will identify these five things, then this is called problem definition. Then this is called problem definition. And if you, after problem definition is planning, okay? Problem definition is the planning task. Before designing an algorithm for that problem, you normally define the problem. That is called problem definition. And in the problem definition, you normally define these five things on a paper. Then how we can solve a state space problem? Then how we can solve a problem simply? Then the first thing that you have to do is to you have to identify your goal for that problem. That is called goal formulation. Form, build, huh? So from form, you have the word formulation. So you have to identify, you have to build, you have to design, you have to search what is your goal in that problem. So when you will determine a new goal or a goal in your problem, that problem, when you will build an algorithm for that problem or program for that problem, that would be called agent. Okay, that would be called agent. So this is the first step. If you are going to solve a state space problem, you have to determine the new goal. You have to determine the goal. You can remove this word new goal. It is ambiguous. So you have to determine the goal for the agent to pursue, to do something further. Huh? So what is goal formulation? You have to identify the goal in that problem. And then problem formulation. Step number 2, problem formulation. In problem formulation, you have to identify what are the actions you have to take and what are the states you have to consider. So between the initial and the final states, what are the states you have to identify? And what are the actions you have to take from initial state to the next, to next, to next, next to next, up to the goal state? What are the actions? So identifying actions and the number of states in that problem is called problem formulation. The goal will be given because this is what you have to identify in the first step. And then search. When you will have the initial state and also the final state, and then if you have identified all the states in that problem, and if you have identified what are the actions you can take from one state to another, then you have to do what? You have to search the solution. Okay, you have to search the solution for that problem. So that's why you can start from the initial state, and states can be any in any direction, but solution would be on some path. Like you are searching in a graph, huh? So you have many paths, but there the solution would be along some path. So from that state to that state, that state, that. So maybe like that, there will be a solution from initial state to the final state. You can imagine a graph with nodes in your mind, and then you can see, okay, there are many solutions possible, but there would be many does not mean that it is not finite. There is a finite number of solutions possible, maybe 2 solutions, 3 solutions. And that solution will do what? It will have a sequence of states from initial state to that node number 7, from node 7 to node maybe 15, from node 15 to maybe node 20. So you will have some sequence of states. So in the search step, you have to identify that sequence of states by using the sequence of actions. When you will have a sequence of states, then you will say, okay, from the initial state, I will perform this action and I will reach on node 7. And on node 7, I will perform this action and I will reach on node 15. And on node 15, I will perform this action and I will reach on node 25. So you will have a sequence of states, but again, you will have also a sequence of actions. So in this third step search, you have to identify the sequence of actions or sequence of states for the solution. For the solution. So when you will identify that sequence, what actions you have to take from initial state, and then you can reach on the final state. When you will identify that sequence of actions, then the next step is execution. You have to execute those actions.
So, I think it is better to do search after that problem selection because we search in sales, we look for action, and the problem formulation, we decide what action is
No, problem formulation is not that one, okay? So formulation normally means if you have a problem, what is the total number of states and what is the total number of actions in that? This problem formulation doesn't mean that you will identify the sequence. No. How many total number of actions and how many total number of states available in that problem? So that's why you only have to yeah, previously in some topic we said fully observable environment, huh? And at in that definition we said that the agent can access all the states in the environment. That is called fully observable. So here in problem formation you will have to identify all the states, and between the states actions are possible. So what are the total number of actions and states possible? That just identifying, it is not for the solution, it is not for the solution, okay? But this search is for the solution. And then when you will have that search done, when you will have that sequence of action, then you can execute that sequence. And when you will execute that sequence, you will reach on the final state. So that's why it is written there. Now you have to carry out this DSA. DSA means so sequence of, okay, desired sequence of actions. Desired sequence of action, DSA. Simply, we are simply calling it. So this is a rough idea. This is a rough idea to solve any problem algorithmically. If you want to build an algorithm for any problem, then these are the steps that you have to consider. These are the steps. Here order is good, but if you will write this search here and this here, no issue, because here this is not an algorithm. Here we are saying that you have to consider these 4 steps, okay? But the order which is given here, that is okay, no issue with that. Okay, no issue with that. But if you will change, okay, no problem. No problem. So these are the 4 steps if you are going to write an algorithm for any problem in AI. So let's move on. And now here, we said here in this, on this slide, we said that, okay, any problem will have state space, okay, no issue. So that's why we will call it a state space problem. But if I will give you a problem and if I ask you to define this problem or give me the problem definition for this problem, then what you have to do, I already said to you that when identifying these 5 things, writing these 5 things about any problem is called problem definition. So now here, so that's why we are taking a Romanian problem and then we are going to define its state space problem definition, or you can say problem definition simply. So here this slide is about problem definition of a Romanian problem. What is Romanian problem? If you will read your textbook, which is given in the introductory document, there is a case study given there. So this is the map of Romania, okay? And the agent is here at the city Arad. This is the city Arad, okay? So this is the city. I can clear it. So this is Arad and the agent is here at this position. And the agent has to go from this city to another city, which is Bukharas. This is the goal state in that case study. In that study, this is the goal state. And all the states in that, all the nodes, all the cities in that state is the total number of. So 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 this is the goal state. We have identified goal. For example, here goal formulation, identified goal. Okay, goal is this one. And after that, problem formulation. Problem formulation is what? Deciding about the states and actions. So this is the total number of states. I can write all the states: Arad, Serend, Oradi, Sibiu, Fagaras, Limniku, Vilsia, Bucharest, all that, by writing all that on the paper. This is the total number of states. And then I can write that I can go from Arad to Oradi, I can go from Arad to Sibiu, I can go from Arad to Timisoara. And then from Oradi, I can go to Serend, I can go to Sibiu. And then from Sibiu, I can go back to Arad, I can go back to Oradi, I can go back to Fagaras and Rimniku Vilsia. In this way, you will have to write all the actions. Okay. When you will write all the actions and when you will write all the states, that would be called problem formulation. And then search, looking for a desired sequence of actions. Search. So you have to search the solution. So there is one solution, which is this one, going from here and then here and then here and then here and then here. This is one solution. The other solution is from here to here. I can change the color, but leave it. Okay. So, and then here, then here, then here. This is another path, huh? Solution. Another solution is I can go here, this way, this way, this way, this way, this way, and then this way. And the other solution is like that, and here, from here to here, this. Four solutions, huh? Four solutions. So four are here, maybe five or whatever. So four solutions are there. But if you will add these values, which are the path cast, which is given here, this is path cast, okay? From one city to another city, the path cast is given. If you will add them, then this route, actually this route is the shortest one. This is the what? Shortest one, if you will add them. And this is our desired. And this is our, and what are the actions? Going from Arad to Sibiu, then Sibiu, going from Sibiu to Rimniku Vilsia, then Rimniku Vilsia to Patisti, then Patisti to Bucharest. Writing all these actions is the search for the sequence of actions. And then at step number 4, you have to execute all these actions. And when you will execute these actions, you will reach on this goal, Bucharest. So this is how. Now, I'm not going to write an algorithm. First, I'm going to give a problem definition for this problem. Problem definition for this Romanian problem. And what is the problem definition for the Romanian problem? We have taken the understanding of this one, but the problem definition is what? Identifying these 5 things: starting state, goal state, set of actions, set of states, and the path cast. Identifying these 5 things about a problem is called problem definition. So this is easy. Now, so problem definition for this Romanian problem is, what is the initial state? Initial state here, according to our discussion, is Arad. So you can write only Arad, or you can say, okay, in Arad. Okay. This is the format only, nothing else. Okay. You can write directly Arad. But in your book, this format is like a algorithmic format, huh? So initial state is agent is in Arad. So this is the initial state. You have to identify 5 things: initial state, goal states, set of actions, or you can say what are the actions and what are the total number of states. This is the 4th one, and the 5th one is path cast. You have to identify 5 things. So okay, initial state is done. And what is the goal state? Bucharest is the goal state. It is given in the case study. Yeah, Bucharest is the goal state. So that's why I can write in Bucharest. when the agent will be in Bucharest, that would be the goal, huh? That would be the goal. So when the goal would be given to us, that is called explicit. Okay, explicit goal. So it is given in the problem. But if you have to find the goal can be changed during the running of the problem. If the goal can be changed, then that goal would be called implicit goal. And like for example, in chess, you don't know where the checkmate will occur. Huh? In playing chess, you don't know at which position the final checkmate will occur. You don't know. So that's why that is implicit property. So in the goal, you have to identify the goal of the problem. And for this problem is Bucharest. Okay, two things are done. Three things are remaining. Actions, states, and path cast. Okay, then what are the actions? What are the actions of this problem? Going from one city to another city, from Arad to Oradi, from Arad to Sarend, from Arad to Sibiu or maybe, from Arad to Timisoara maybe. So if you will go, or if it is a taxi, then you can write drive from Arad, and then it would be equal to what? Sibiu. You will reach to Sibiu. For example, how you can write action is what? It is written here, but you don't have to worry. Okay, it is written like in this format, but you don't have to worry. For example, what it means? It means you have to find actions at state S. For example, here at Arad, what are the actions available at that Arad? One action is going to Sarend, other action is going to Sibiu, and other action is going to Timisoara. Only three actions are available on this state. Only three actions are available on this state. So in this way, how you can write these actions? So you are writing actions on Arad. So actions when the agent is in Arad, huh? When the agent is in Arad, what are the actions? The agent can go to Sibiu. The agent can go to Timisoara. The agent can go to Serend or Zerend. So these three actions are available here, huh? So how you can write? You can write in this way, or you can write in any format. Okay, you can write in any format. You can write actions in Arad, and then you can write Sibiu, Timisoara, Serend directly in one line, huh? Similarly, then you will take any other from Serend. What are the actions? One is back to Arad, other is to Oradi. Two actions are available. Similarly, from Fagaras, what are the actions? One is back to Sibiu, other is to Bukharast. In this way, you have to write all the actions. This is planning. This is the problem definition. You have to write all the actions. But here only one example is given, huh, for understanding. Okay, now I hope that you have this understanding of this actions. Now, what are the
action for that?
yeah, you have to write every action for this problem. So this problem has many states, so you have to consider all states. And what are the actions available there? What are the edges available? These edges are the actions actually. Now, the fourth thing, what are the total number of states? What are the total numbers of states in that problem? Or called transition. Transition means moving from one point to another. That is called transition. How you can write here according to your book? So we can write result. Or you can write this word result, or you can write transition. The word transition you can write here. So result, what is the result if the agent will go from state S and you will perform the action A? This is the meaning of that. This is the meaning of that. I can remove all that drawing and I can explain it later. So we are here. How you can write the transitions? So in this way, you will write result and then state S and the action that you will perform on this state S. When you will perform this action on this state, you will reach on the next state. That's why it is written here, the successor state, the next state. Successor means next state. So this is a kind of a formula is written there. And then you can apply this formula over the whole problem. So, okay, when you are in Arad, so now apply this formula here and calculate the transition for that. So when you are in Arad, how I can write it by using this? So result state is what? State is agent is in Arad. This comma, okay, comma. And what is the action? There are three actions available. Go to Serend, go to Sibiu, and go to Timisoara. But here you are writing go to Serend. And when go to Serend, what will happen? If you will perform this action, you will reach on this state. You will reach on this state. So that's why is equal to the next state would be what? Agent would be in Serend.
Must write every step.
Yeah, every step. So every step. This is only one example. And in this way, you will write result in Arad, and then the next is go to Sibiu, and then you will reach what? In Sibiu. Similarly, result in Arad, go to Timisoara is equal to what? Timisoara. And in this way, you have to consider all these nodes. You have to consider all these nodes. And then you will be able to write all the transitions. This is the fourth step.
What is the benefit? What is the benefit from this step?
This is the planning. Benefit is then you will get the complete understanding of this problem. These are the 5 steps. If you will perform these 5 steps, then you will understand what you have to do. So you are defining the problem. Problem will be given to you and you are defining the problem. Defining some means, yeah, okay, you are describing. And when if you are able to describe anything, it means you have the understanding of that. So now the fifth component, according to this diagram, fifth component, this one, path cast. So what is the path cast? So this, all the values which are given here between 2 states are the path cast here in this problem. For example, from Arad to Serend, we have the value 75. This is the path cast for it. And similarly, 71 is the path cast from Serend to Oradi. And from Oradi to Sibiu, 151 is the path cast. For this problem, this is the path cast. For this problem, this is the path cast. For a different problem, path cast can be different. Okay. Here the path cast is given. So path cast is what? It is the sum of the step cost. This is called step, one step. Going from Arad to Serend is one step. Going from Arad to Sibiu is one step. But if you, and this one step, next steps, now this is a sequence of step which I am taking.
You are going to make it in the first one or just and from Arad to Sibiu?
Yeah, if you have to reach from Arad to Bucharest, and there are many solutions possible, and then you have to, one solution is this one, so you have to sum up all these values. Yeah, till the Bucharest. You have, similarly from here to here, you will have to sum up all the values. And when you will sum up the whole, all the values, only then you can find what is shortest. What is shorter. Anyhow, what is the path cost? The formula for here is, it is the sum of the step cost. Okay, the formula is C for cost, and S for state. Your agent can be at any state, and then you will perform the action, and then you will perform the action, and then you will reach on the next state. S prime, X prime means next state. And when you will reach, you will use some cost C. So this is the formula that you can use for the problem definition, for writing the definition, okay?
What is meaning is
S prime or S slash, the next state. So for example, here, the cost from this S is what? I am writing shortly, okay? From Arad, action is what? Action is what? Go to, go to, yeah, go to Srind. And then S prime would be what? Srind, okay? S prime would be Srind. And that cost would be what? Is equal to 75. This is the way, huh? So this is the cost. So now path cost. Normally path cost means path cost means okay, the path from the initial state to the final state. Normally it means, because it is a path, not a step cost. What is step cost? This is one step. This is one step. So that's why the whatever the cost is 75, this is a cost for the step, one step. But if you have this path, which is a solution, then you can add, you can sum up all these values. Then it would be called path cost. Okay. So it can be, the path cost can be sum of distances as it is here, or the number of action. If there are no distances, distant values are given, then you can also count the number of actions. You have to deal with the problem. So now these 5 things are defined for this problem. And now this is the problem definition for the Romanian problem. Clear? So now moving next. Write down this problem definition or SSP definition for the vacuum cleaner agent that you have studied in previously. What was that? If you will go there, this was. It will have 2 locations, square A, B. It can perceive what is the location and is there any dirt in it. This is the percepts. What are the actions? Left, right, suck up the dirt or do nothing. These are the actions. Okay, now you can come back here. And now, because now you have a background that what is. So you have to assume the same problem of vacuum cleaner that you have studied before. You have to take the same information from that problem that you have studied. So now we have to write problem definition for the vacuum cleaner agent, our word. It means what? Problem definition means what? You have to write 5 things like before. So you have to mention initial thing, goal state, initial state, goal state. What are the total number of states? Or what are the actions available in that problem? Or what is the path cost? This is what 5 things you have to define. So if you will see this picture, so then you can see that this is square A, this is square B, and agent can be here in square A or it can be on square B, or the dirt can be in square A or the dirt cannot be present, huh? Similarly, the dirt is present in location B, but it cannot be present in location B. So there are 4 or 5 different possible initial states, huh? So then what initial state you will give? I don't know. And from these 4 or 5 different initial states, what initial state you can take? We don't know. So that's why the initial state is what? It can be any state. It can be any, huh? From those 4 or 5 different states, it can be any state. Because there is no some particular one. We don't have some particular one. So these So, so initial state is what? It can be any state. And what is the goal state? We want that all these squares should be clean. All these squares should be clean. So that is our goal. That is our goal, which you can see here. So here, no dirt. Okay, either the agent vacuum cleaner is in square A or square B. Okay, no issue. But all squares are clear. So that's why the goal state is what? No dirt in any location. You can write it. We don't want a dirt in any location. This is the goal state. Okay, now the three things are remaining: states, actions, and path cast. States, from one state to next state, from next to next, from next to next. So when you will consider the states, so then this diagram is possible. Because now you are considering here the number of states and the number of actions. Number of states and the number of actions. What are the actions? The agent can go to the left, to the right, it can suck up the dirt, or it can perform no any operation. Okay, this is defined in the information of the problem. So you can write action that these are the actions. And what are the states? What would be the states in that problem? The dirt and the robot, which is this agent. Okay, the dirt and the robot could be in any location. Could be in any location. So you can so you can so you can now write dirt in any location and robot in any location. This could be the possible states. But if you have to draw the diagram, you cannot write something like that. Here, okay, you are defining a problem, so okay, you can write some sentence. But if you have to draw if I say draw the diagram, then you cannot say something like that. You have to draw. Okay, then you can start. Okay, suppose you are starting from here, that the two squares having the dirt, and your agent is and your robot is at square A. And according to the vacuum cleaner word, if the vacuum cleaner agent will find the dirt, it will do what? According to that previous algorithm, huh? If it will find dirty, it will start sucking, the first condition. If there is no dirt, then it will see if it is location A, then performing right. And if it is not location A, and if it is B, then performing left. So now we have to, so this is called what function? This is the action function for the agent. Now we have to do something according to that. So now this is the situation. What are the actions? If so, this left, right, suck, no operation. You can consider all the functions at this state. I can perform. So now your agent is on square A, and if you perform left is on this direction, then it will not go out. Okay, that is not, we are not considering this condition that it will go out of the environment. No, if you will perform left, it will remain same at the same location. Okay, if you will perform left. If you will perform sucking, this dirt will be finished. Huh? If your agent will perform sucking, this dirt will be finished. And you can see, then this would be the next state, S for sucking. And then this would be the next state, no dirt here. This would be the next diagram. And if you will perform the action move towards right, then this is the right side. And here R, you can see this R, move towards right. And then this agent will go towards right without cleaning it. So these are the possible states after performing the actions on this state 1. Okay. Now, if you are here, now this is finished. You have considered all. Now look over here. So if you will perform right, you will, so this is the loop, which means you will be here. The agent would be here at the same location. And if the agent will perform sucking, the sucking, and here you can see this dirt will be cleaned. And you are not seeing any dirt here. This is the next diagram after sucking. And what action left? Right, sucking, left is left. And if you will perform on this state, if you will perform left, okay, this is the left. Then the robot will move towards the other location. So that this is the previous state. Huh? So that is clear. So now you can see these states. So these two are now clear. These two states are now clear. Similarly here, if this is the situation, if you will perform left, okay, you will remain here. If you will perform sucking, as there is no dirt, so you will also remain at the same state, huh? Because there is no dirt. No dirt. So the agent will also be there, but there is no dirt, okay, you will be in the same state. And that is that state. And that is that state. And if you will perform right, this agent will move toward the right side, and this would be a new state. And this would be a new state. So now this is clear. Similarly, you can see all these states, and it is very much clear. We are only seeing now this one. Suppose that we are here, and if you will perform sucking, the robot is here, dirt is available, so dirt will be clean in the next. You don't have any dirt. And if you will perform left, you will remain here. And if you will perform right, you will go here. This is the next state. So this is an easy picture, huh? You have to, here in this diagram, you are covering all the actions. And then you are drawing all the states which are possible for vacuum cleaner agent. But you can write these states and actions like that. Dirt and robot locations. Total number of dirt locations and total number of robot locations or agent locations. And what are the actions? You can see left, right, sucking, or no operation. But no op is not here, okay? You are considering only left, right, suck. What is left? Path cost. Here, how you can calculate the path cost? We are not given with any cost or something like that. So here you can do what? When you will perform one action, you can reward 1 point to the agent, to the robot. For example, if you are performing left, you are performing one per action. You are giving 1 point to that agent. If you are performing right, you are giving another one to the agent. And if you are performing sucking, you are giving another one to the agent. And then you can sum up all these actions, 1 plus 1 plus 1 plus 1. In this way, you will calculate the path cost. And if you are not, and if robot is not performing anything, okay, then you can give it 0. If agent is not performing anything, then you can give it 0. For example, here, but then you have to check. For example, here, the agent is performing left action on this state. But here, the agent is still at the same location, not performing anything, huh? So you will award 0. But if you will perform right, it will go to the right. So the location is changed. So that's why you can assign, okay? But this is not optimal. This is not optimal. Optimal is what? If you will perform sucking, and then you will award 1. Even moving on the left or moving on the right, you can assign it 0. But these are the conditions, then you have to write it in the algorithm. But at the moment, in the beginning, we are not going into that much depth in the beginning. So defining these 5 things for this vacuum cleaner, this is called the problem definition for the vacuum cleaner agent. Now, problem definition for 8 puzzle. What is 8 puzzle? Normally, when you were kids, this is the thing that you will have. The blocks were there. One of your friend will move it randomly, and then it will he can give it to you, and then you have to arrange those blocks. And you have to, for example, this is the random position. Now you can move this block down, and then this space will be empty. You can move this there, then like that, huh? And then you, so this is the this any random state can be the start state, and then when you will arrange, you have to arrange it like that: space in the beginning, and then 1 2 3 4 5 in ascending order. This is the goal state. This is called 8 puzzle, because here you have 8 blocks from 1 to 8. This is called 8 puzzle. Now write the problem definition for that. So now we are going to write the problem for definition for this 8 puzzle. So starting state. Starting state. Is there any fixed starting state for this 8 puzzle? No. So it could be random, huh? One person can, so it could be random. This is not the only start state. Any other friend of mine can give me any other state. So that's why the initial state can be any state, or you can write any random state. Any random disordered state would be the initial state. And what would be the goal state? Goal state equal to the given in the goal state. Okay, equal to this diagram. This is the goal state. All blocks in order and space is in the beginning slot, you can say, in the beginning block. If you want to write it in words, you can say space in the beginning, top left upper corner, and all blocks would then be in ascending order. Okay, so that would be the goal state, not goal test. Okay, this is an ambiguous word. Goal state. Now, 3 things are remaining: action, states, and path casts. So then, states. This is one state. This is one state. This is another. So these are the states, huh? Every block is a state. But when you will change even one block here, now you will have new states. So anyhow, but here in this 8 puzzle, the state means the state of the whole game. Okay, the state of the whole game. For example, now in this picture, 7 here, 2 here, 4 here, 6 here, 3, 8, 5, and space in between. This whole picture is one state which you are looking at. Okay, with the proper position of each block. Here the 7 is in the top left upper corner, 4 is in the top right upper corner. So this pattern, you can say, is one state. When I will move this 2 here, then the picture is changed, huh? Then this whole picture is a new picture, and then this is another state, and this is another state. So in this way, you can consider that there are many different possibilities of different states. And how many rows and columns you have? 3 cross 3. So then you can write any number of 3 cross 3 matrix of any. So here you can write any. By the way, any is not a proper word, because if you will calculate the possibilities, then you will have fixed amount of what? possibilities. If you will calculate it through some algorithm, then you will have the fix, sorry, then you will have the fixed amount of possibilities in that game. So that's why any is not a proper word then. So so then so then a 3 cross 3, 3 rows and 3 columns matrix of integers. So we have a 3 cross 3 matrix of integers, and this is what a 3 cross 3. So this is a 3 cross 3 and it is one picture. When you will change, it will still is a 3 cross 3 matrix, huh? But the picture is changed. So then states what? You can say all the different possibilities of 3 cross 3 different 3 cross 3 matrix of integers. Hmm? Yes, this is okay. Matrix of integers because you have these integers here 1, 2, 3, 4, 5. So any is not a proper word, but all possibilities, that is okay. So this is the states. And if you have to write all the diagrams, if you have to show all the states in the diagram, it is not possible here for this on this slide. Okay, it can be many. Okay, it can be many. So then okay, states is done, and then actions. What is action? So here, if I say move this 6 to the left or move this 5 to the right, this is not a good approach to write. Then what I will move? So I will consider this space as a controller. Huh? Moving this space on the top or down or right or left. This is what you can say. Okay. This is what you can say. So move the blank space left on the left side, right side, up and down. These are the actions. These are the actions. So when you will move this 6 here, so you are moving this blank on the right. Hmm? And when you are moving this 2 here, you are moving this blank over the top on the top position. So this is how we are writing these actions. And path cast is what? When you move this blank space or this blank block, when you move this in any on any direction, when you move it one step in any direction, so then you will have one unit or one cast per move. That is called one cast per move. And in this way, and when you were a kid, you were playing this game, and your friend told you this many times that I have solved this game in 4 steps. Solve it in 3 steps, like that, huh? So, so, so that is why he was saying, because that 3, that 4 is his path cast, and now you have to search the path cast 3 with that move. So path cast is 1 per move. Okay, in this way you can go on with this. And these are the 5 components for the definition of this 8 puzzle problem. Now, 8 queen problem. So problem definition for 8 queen. So this is a picture for the 8 queen. You have 8 queens. You have to place. What is this problem? So you have to place these 8 queens. Here only 7 are shown. 1 is left. Don't worry, this is not a solution. You have to find that solution by yourself. So this column is empty. You have to place this eighth queen by yourself. Okay. So that's why this is an incomplete picture. So what this 8 queen problem is, you have to place these 8 queens on the chessboard, and the goal is none of these queens will attack each other. Okay, none of these queens will attack each other. So for example, they are not attacking each other, they are not attacking each other, or they are not attacking this one each other. You can check, they are not attacking each other. So this is what the 8 queen problem is. You have to place, you have to put 8 queens in such a way on the chessboard that none of the queen will attack each other. This is a problem. And now you have to write the problem definition for it, for this. What is the initial state? Initial state, no queens on the board. Board is empty. Board is empty, and we have not placed any queen on the board, so that is the initial state. What is the goal state for that? You will put 8 queens on the board, and none attack. No any queen will attack to other. So this is the goal state. This is what you want. Now the 3 things are remaining. States. So any arrangement when you will have 0 queen on the board, that is initial state. That is a state, but that is initial state. And at some point you will, so any arrangement of 0 to 8 queens on the board is a state. So any arrangement, if they are attacking, that is also a state. If they are the goal state in which all the queens are not attacking each other, it is also a state. And in between, when two are non-attacking, others are attacking, this is also a state. So with a minor difference of one move, it is a state. It is a state. This whole picture of the game is a state with a minor difference. So there are too many possibilities of states here in this problem, even more than that 8 puzzle. So any arrangement of from 0 queen to 8 queens on the board is a state. Actions. What actions you can do? Adding a queen to any empty square, okay? Or placing a queen on any empty square. When you, okay, I will discuss it later. Add a queen to any empty square. This is a action. For example, here, this is empty. When you will move this queen to here, this is action. When you will move this queen to here, this is action. Any empty square. Like you normally play in chess, So that is a action. And what is the path cast? When you will move, one per move. Move. That move could be from here to here. That is one move, And this is a queen. It can go by passing more than 2 cells, So one per move. This is one approach. This is one way to write the problem definition for the 8 queens, and this is called complete state formulation. Complete state. Why it is written like that? Because here the player is doing what? The agent is doing what? In the beginning, the chessboard is empty. In the beginning, the chessboard is empty. And then next, he's placing all the 8 queens on the, he's throwing, he is placing or throwing whatever, all the 8 queens on the board, but in some blocks, in some different blocks. And he's not caring that either they are attacking or not. Maybe, for example, initially it was empty, and then I throw all the queens on here, and I move only one in this top left upper corner. The rest are just random. The rest are just, don't consider this picture. Maybe this is here, this one is placing here, this one is placing here, maybe just random. So that would be a state. And then I will do what? I will think, and then I will move another one here, or I will move another one here randomly. This would be another state. So here I am doing the things randomly. So this approach has the title complete state formulation. And if you will think, so when the board is empty, I have 8 rows, 8 columns. How many possibilities? 64 blocks are available for me to start with. And then when I placed one queen in proper position, then what? One cell is now gone from that 64, and you have only 63 left. And then when you place the second queen in a proper position, then 2 cells are now gone from that 64. And what is then left? 62. And in this way, when you are putting your queens, and then the remaining blocks would be up to 57 for the 8 queens. You can go like that. And when you will multiply all these, it will be 1.8 multiplied by 10 raised power 14 possible sequences you have to investigate for finding the proper positions. So these are so what it means? It means 1.8 and 14 zeros. So you can say 1, 8 and then 14 zeros on the right side. This is what it means. Okay. 1, 8 and 14 zeros. This is what it means. And this is how much big figure, big digit that you have to find these possible sequences. Then you can find the solution for that. Solution for that. Now, in the other approach, which is called incremental formulation, this is a different approach. And in this approach, what you have to do? So initially the board would be empty. So you have to start with the empty state, and you have to add, each action will add what? It will add a queen to the state. And what is that state? Here we are not writing all 5 components. The rest of the 3 are same. Only these 2 are different. So that's why only these 2 are mentioned. The rest of the remaining are the same. States for this incremental approach, if you will go incrementally, what is that? 1 per column in the leftmost columns. What you will do? Initially it would be empty. Then you will do what? You will take the first queen, you will place it, okay, in the left column. This is the left column. In the first left column, okay, you will place it at the top or at any position, but it is always good to place it at the top because no any other queen is there. Then you will take the second one, and you will think only in the second left column that what is the position that where you will place it, so that it will not in your attacking position. You will think this, no attacking, here attacking, here attacking. But if you will place it here, non-attacking. So you will place it here. You will not think in the whole, all the columns. You will think only this column. This is the second increment. Now in the third increment, you will take the third queen and you will think only in the third column. Left third column. So can I place it here? No, attacked. 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 Can I place it here? Yes. Okay. This is the third, then fourth, then fifth, sixth. Similarly, 7 and 8, you can think like that. This is called incremental formulation. This is called incremental formulation. And here you will think one per column in the leftmost n columns each time. And you will, with no queen attacking another, this is what you have to consider. And then action would be what? Action would be the same, adding a queen to any square, in the leftmost empty column by making sure that no queen is attacked. So these are the states and actions in this incremental approach. And if you will go with this approach, then how many possibilities that you have to check? Only 2057. Not like this, which you have seen here previously. Too many. 1, 8, 14 zeros. This is too much. But with this approach, you will have only 2057 possibilities that you have to check. So anyhow, so states, actions, okay, this is action and this is states. Only these two are different here in complete state and incremental. The rest of the thing, initial state, goal, path is same for both. So I can ask you to write a incremental problem definition for 8 queens, then you can consider this part. And if I will ask you write the complete state form problem definition for the 8 queen, then you will consider this part. Okay. Similarly, problem definition for airline travel website. This is what you can read it by yourself. Consider you are on a Saudi airline website and you are going to book some flight. So consider that whole website a agent. Then what would be the states? What would be the initial states? What would be the actions? What would the goal state, path, cost? So I have highlighted in red which are the main idea, and it has further additional ideas also. So initial state, what if you are using the website, you have to type some query on the website. Initial, you will give that what would be your starting location, what would be your starting airport or departing website airport, departing airport, or you can say from which you are. For example, if I am going from here Medina to Pakistan, maybe Islamabad, so Medina is my departing airport. This is my initial state, and Islamabad is my destination. So initial state, so that is what it is mentioning. And goal state is what? Arrival airport, where I am going. Okay. That destination. It would be specified by the user on the website where you are going to search where you are going to book a flight. What would be the states, locations, an airport, and the current time? The states can have extra fare basis, economy, business, something like that. Domestic traveling or international, these can be extra. These can be extra information in the states. But actually the states of this agent would be what? Locations and the current time. Normally, if you will go with the Saudi airline to your country, it will first go to Jeddah, Riyadh, Jeddah, Riyadh, and then it will go towards your destination. So this is normal, I think, for all of us, So then what? So that mid is also a state, initial is also a state, that final is also a state. And if your traveling is long, then you will have further locations in between. Similarly, action. Action is what? Taking any flight from my, you can say, normally we have a short journey, so that's why we have only, you can say, taking from Medina to Riyadh, and then Riyadh to taking flight from Riyadh to Islamabad is action. Or if it is a long journey and there are many, 4 or 5 different countries involved, you have to write all those cities of those countries are the states. Path cost. So you are paying from your starting to ending. You are paying. That is your path cost, huh? So depends on monetary cost. Monetary means the things in which money is involved. So that's why monetary. Or waiting time, or flight time, total flight time. So these could be the things there. So this is the end of uh, this CLO1. And now we have a CLO2. Do you want to start it? Next lecture. That's why I asked you, because I know your psychology. I know your mentality. You never say, yes, continue with the CLO. No, it is not possible with the students, huh? So anyhow, okay, I am stopping here. Next in CLO, inshallah.